Students, this is lesson U6A08. By the end of the lesson, you should be able to say I can solve circle proofs. So this is actually the last lesson of the unit, and just to recap all the different things that we've talked about involving circle geometry, here are the theorems associated with the things that we've talked about, excluding the arc length formula and the area of a sector formula, because that's more for like problem solving. And here we're trying to create, for the problems that we're looking at in this lesson, we are trying to prove geometric relationships instead. So we're not really like solving a problem per se, but we're trying to prove geometric relationships. Here are the theorems, okay, that we have that we had used to make many of the arguments, to make many of the algebraic arguments. That the central angle and the intercepted arc will have the same measure. Congruent central angles will have congruent arcs. Congruent chords will intercept congruent arcs, and vice versa. And congruent chords will be equidistant from the center of the circle. Here are some of the theorems that we had used in maybe 3 lessons ago. Okay, inscribed angles intercepting congruent arcs are going to be congruent. The triangle inscribed in a semicircle will always be a right triangle. Opposite angles of a quadrilateral inscribed in a circle will always be supplementary. And parallel lines intercept congruent arcs. Tangent lines that meet outside of a circle are going to be congruent. And last but not least, and this is super important for a lot of problem solving as well as for proving different relationships, a tangent line and the radius of a circle will always be 90 degrees. Let's take a look at the first proof together. So what I have here is a quadrilateral that's inscribed inside of a circle. I have AB is parallel to CD. The task is to show that triangle ACD is congruent to triangle BDC. So what you're going to do, okay, let's pause the video for a moment and try this out on your own. Draw over this. See if you can make certain arguments come out. So hopefully you guys had some time to think about this. So we know that AB is parallel to CD, right? So immediately, okay, if I know that these two lines are parallel, these arcs must be congruent, because parallel lines intercept congruent arcs. And if congruent arcs are present and there are chords present, then therefore these lines, these chords must be congruent, because congruent arcs intercept congruent chords. So now what I have is, okay, I have a pair of sides I can talk about. I'm trying to prove triangle ACD. I'm trying to prove triangle ACD is congruent to triangle BDC. So I'm almost there. If you notice, okay, triangle ACD and triangle BDC share a common side. They share side BC. DC is shared between both triangles, so that is another side that's going to be congruent. So now I have two sides that are congruent. But wait a minute. Also, isn't this an isosceles trapezoid? Right? What are the requirements for a quadrilateral to be an isosceles trapezoid? Well, it is we have a pair of sides that are parallel, and the non-parallel sides are supposed to be congruent to one another. So therefore, BD and AC should be congruent, because diagonals in an isosceles trapezoid must be congruent. So we can prove triangle ACD and triangle BDC to be congruent based on side, side, side. If that doesn't work for you, there are alternate ways that we can approach this, okay? We can also try to do this using, we can also try to prove this using other methods, like angle side angle or side angle side, but I think this is going to be a proper way of approaching this. So let's take a look. BC is congruent, arc BC is congruent to arc AD. We recognize this because, again, parallel chords intercept congruent arcs. We also recognize that chord BC and chord AD therefore must be congruent because congruent arcs intercept congruent chords. Quadrilateral ABCD is an isosceles trapezoid, so I went a little out of order, and that's okay. So quadrilateral ABCD is an isosceles trapezoid. Why is that? Well, that's because a quadrilateral of one pair of sides congruent and one pair of opposite sides parallel is an isosceles trapezoid. So recognizing that this is an isosceles trapezoid, we can then therefore declare that DC, oh, actually, no, I take that back. DC is congruent to DC because of reflexive. AC is congruent to BD. Well, that is because those are the diagonals of the isosceles trapezoid. So that's because of line 4. So diagonals of isosceles trapezoids is congruent. And then last but not least, since now we have side, side, we can say triangle ACD and triangle BDC are congruent because of side, side, side. Pause the video to see if you can tackle this. Again, it's very, very similar. Okay, hopefully you guys had some time to think about this. So AED is a diameter, and we have arc AB is congruent to arc CD. Let's put that into the given statements. Okay, so recognizing that arc AB is congruent to arc CD, I can then declare that chord AB is going to be congruent to chord CD because congruent arcs intercept congruent chords, or congruent chords intercept congruent arcs. I also recognize that this angle over here must be a right angle because any triangle inscribed in the semicircle will be right triangles. And I also immediately know that EAD must be congruent to itself because that side is being shared. So immediately I know triangle BDA must be congruent to triangle CAD because of hypotenuse leg, right? Because this length right here is the hypotenuse. CD and BD, those are the legs. Those are right triangles there. They must be congruent because of hypotenuse leg. And then I have another pair of triangles I need to prove congruent here. I have BFA congruent to CFD. So no worries, okay? I know that these two angles must be congruent to one another because they are vertical angles. And since I have vertical angles there, and I have angle B congruent to angle C, those are another pair of angles. This is going to be the triangle BFA and CFD are going to be congruent because of angle, angle, side. Let's take a look at this now. So one of the first things that we had established was that angle ABD, I did not say this first, actually I said this later on in the proof, but this does not require any prerequisite information that's not already present in the proof. So angle ABD and angle BCA are right angles because angle is inscribed in semicircle is a right angle. Next, we can say that angle ABD is going to be congruent to angle DCA because of all right angles are congruent. Next, we can say that AB is congruent to CD because congruent arcs intercept congruent chords, or congruent chords intercept congruent arcs. Next, we can say that angle BFA is congruent to angle CFD because of vertical angles. So I went and actually proved this first. And next, we can say that triangle BFA is going to be congruent to triangle CFD because of angle, angle, side. And we're almost there. We can say that AD is congruent to itself because of reflexive, and that is the hypotenuse. So therefore, we can say triangle BDA must be congruent to triangle CAD because of hypotenuse leg. All right, let's take a look at another example. Pause the video here to see if you can figure this out. So let's try to draw all over this. So I know that AED is the diameter. I know that CD is a tangent. I know that angle C and BDA, they're congruent to one another. Angle C and angle BDA are going to be congruent to one another. So C and BDA are congruent to one another. Okay. And this is going to be tangent. So if that's tangent, then that means that's going to be a right angle. Okay? Because it says CD is a tangent and AD is the diameter. Okay. So now that we have this, okay, and we're trying to show AB divided by BD is equal to BD divided by BC. So a little bit of strategy needs to be in place here. If you look at this immediately, right, isn't this the same thing as AB times BC is equal to BD squared? Where have we seen this before? Oh yeah, that's right. This is actually the geometric mean, right? Guys, do you remember this? M, N, and L, right? What's the relationship? M times, I'm sorry. I think I wrote like this in the previous lesson. I said L, M, and N, right? L times M is equal to N squared. Remember that? Isn't that what the situation is right now that we have here? So this is going to be true because of the geometric mean, right? So actually, if you look at this, right, this is that setup. I have 3 overlapping right triangles right now. And because I have these 3 overlapping right triangles, then this geometric mean must be true. And because this geometric mean is true, then that means this statement is true. And if this statement is true, we can then divide both sides by BC and divide both sides by BD, leading us to this conclusion here. So I just talked through this entire proof. Let's now try to figure out how we can put this into words in the 2-column proof. So immediately I recognize that angle CDA is a right angle. And the reason is tangents and diameter form a right angle. Next, I know that angle ABD is a right angle because inscribed angle in a semicircle forms a right angle. Next, I know that angle CDA and angle ABD are going to be congruent because all right angles are congruent. Next, I know that triangle ABD will be similar to triangle DBC because that is what we're doing here. We are comparing these 2 triangles together, right? So since these 2 triangles are similar because of angle-angle theorem, I can then create these proportions. Because of, well, corresponding parts of similar triangles are proportional. Let's take a look at the last problem here. So I have segment AEC and then segment BED. These are chords. And what we want to do is we want to prove that those proportional statements are true. Pause the video to see if you can figure this out. So what we have here, if you look at this closely, AE over BE is equal to ED over EC. Okay? So actually, AE to BE, so I'm taking one leg to another, is to ED is to one leg to yet another. This looks really confusing, but what we're doing here is we have this proportion set up. therefore implying that these two triangles are going to be similar. How can we show that they are similar? Well, I immediately know, actually, right, that angle A should be congruent to angle B because they both intercept arc DC here. And I also know that angle D should be congruent to angle C because they both intercept angle AB. And the reason for all this is inscribed angles intercepting the same arc are congruent. So I immediately have, what I have is two similar triangles. These two triangles are going to be similar because of angle-angle theorem. And because of angle-angle theorem, I can then set up proportions to say that this must be true. And then the last thing I can do is I can cross multiply to end up with this product here. So let's take a look. So I know that angle ADB must be congruent to angle ACB because inscribed angles intercept same arc are congruent. I also recognize that angle AED must be congruent to angle BEC. This is because of vertical angles. So I chose, in my original attempt at this problem here, slightly different from what I have articulated. So instead of using the other inscribed angle, I use vertical angles instead, which is all the same because the goal is to just get two angles here. So these two triangles are going to be similar because of angle-angle theorem. My fifth step is to show this proportion is true. And this is going to be true because corresponding parts of similar triangles are proportional. Last but not least, I'm going to cross multiply to get that. And the reason is to cross multiply.